So it's my real pleasure, my great pleasure, to have the opportunity to introduce Jan Hall, okay, as our speaker. For those of us that work in photonics, optical physics, atomic physics, Jan really needs no introduction at all. We are practitioners of many of the techniques that he's actually developed over the decades. He is extremely well-known, famous, okay, for kind of pioneering the whole idea that lasers could be used for doing some remarkably precise measurements and kind of pushing that idea to the limit. Along the way, as I said, there's been many ideas and methods that he's developed. Some of them I'm sure people in the audience use routinely. There's a technique I'll mention called the Pound-Reaver-Hall locking technique. It's actually used in the gravity wave detection system, the LIGO system. It's used in commercial systems. We use it in my lab. We have probably over a dozen of these systems that are locking lasers to various high-Q microcavities. But the subject that we're going to hear about today, and that I guess has had a remarkable impact on technology and science, has been the frequency comb. And this is an idea and a technique and a device and a whole set of applications that Jan's group and also the group of Ted Hench about 15, 16 years ago developed and discovered, and then have just pushed forward in all kinds of remarkable ways over the last 15 years. Jan's received many awards, and I'll just list a small number here. Really, is it just a small number, a long list. He's received the Charles Towns Award, the Frederick Ives Medal, the Arthur Shallow Prize, a number of others, and then of course he's also the co-recipient of the 2005 Nobel Prize in Physics for his work on the frequency comb, which he shared with Ted Hench and Roy Glauber. And so we've been really fortunate this week. We invited Jan to participate in our workshop, this Keck Institute for Space Studies workshop that's been focusing on space applications of frequency combs. And so it has been great to have him here through the week and tomorrow, actually participating in the workshop and actually asking lots of questions and pushing us in different directions. And we were equally delighted that he accepted our invitation to give this special lecture today. And so please join me in giving a warm welcome to Jan.
Holy smokes. Thank you. I don't know what the boss lady is going to say, but there is sitting place here in case.
Anybody who wants to come down and sit up front is more than welcome. So just do it now. You've got 30 seconds. There you go. Come on.
And while you're doing that, I'll check out my laser pointer. Oh, this is, that's not the right one. Okay, so let's see here. The place that I live, I think, has a lot to do with having a good spirit. Unfortunately, sometimes it gets cold there, and February was a time of the year that I would buy an airplane ticket and come visit the Kimball Labs here for a long time. I had an absolutely beautiful springtime in Pasadena. I got to see firsthand just on the television, the Rodney King riots, or I could look out the window and see them in real life. So it's a real introduction to California life. Charles Towns is a really important guy in our field. He just had such a marvelous grace about him. I'm not positive that has to do with his religious ideas, but anyway, he's one of the all-time heroes in my life. So we helped the Creole celebrate their 25 years. Now, some university towns are really special. I'd like to call your attention to this one. They sell Glocks and ammo, and if you buy anything, you get a Nobel Prize. So it was a little bit irritating to me because I'd gone up to Colorado State University just after the prize was announced, so this was in the spring after that, and I thought, man, it would be much easier to go to his store and buy something instead of do what I had to do. Okay, So anyway, I don't think there's anybody in here that has any anxiety about being a nerd, but sometimes when I go to the elementary school, it's important to show that I really wasn't so well adjusted. And what about this past tense stuff? Maybe there's still problems. There's some other kinds of problems. But I'd like to show you one of my contributions. The yellow sticky tapes on the glass of a machine that you don't use anymore. Well, what we're going to do today is stand up and try to take a look across 55 years of progress in the laser business. And most of these little valleys are so incredibly beautiful. I'd like to share half a day with you on it. Some of the places I've poked around in absolutely myself. Some of them are just known to me by their reputations. But this picture just seemed exactly right to me to say, this is where we are as scientists. We're standing on the edge and we're looking at something fantastic. We can see it's 10 times more fantastic than we can put into words. And let's get on with it and try to figure out what our part is. So part of my work then is to talk to the young people. And here's a girl that's just discovered neodymium magnets. Don't think she'll ever forget that. She was so happy about it. Here's another young lady that's discovered momentum conservation with the aid of Mr. Newton, and she by herself invented this anti-symmetric mode, and then everybody came around to see how it's working. So what kind of questions does one worry about? In the high school, I'm kind of depressed sometimes because you ask young people, what are you worried about? Well, nothing, or I don't have enough gas for my motorcycle, or blah, blah, blah. But we have some real things to stew about. And when the lasers first came up, our guys and the Russians and the Japanese had different sources of iodine. So we had a little fun trying to see if all our lasers really had the same frequency, and they didn't. Okay, so it's not about the iodine, it's about technical mistakes that we made. And so that was 10 or 15 years. The issue about how narrow a laser line width can be was that I thought it was nearly impossible to reach 1 hertz because CW lasers had multi-megahertz. So I told my wife and my colleagues that, okay, my retirement is going to be when we get to a hertz. But as soon as you get the idea that lets you get to 10 hertz, it already gets you to 0.01 hertz or whatever the thing is. So we'll talk about that. The business at the bottom here, though, I think is really where it's fun, and I'll describe some experiments that will happen in the next year or so. We'll find out stuff that we only talk about now. When I came to the NIST, one of the jobs was for a man to build a photoelectric microscope to measure the scratches on this. That was in 1962. This meter bar was still the subdivision that was used by the National Bureau of Standards. These platinum iridium weights, this is not the K, which is the prototype. That one is kept, and it's only used if the National Bureau of Standards or the people from Korea or another lab want to have their mass checked. Then you clean all of these masses, and every 10, 15 years you do it, and then somebody recently has made a plot of how this is, and it turns out that it looks like all of the representative masses that countries have are getting heavier. Now, can anybody get an idea? When you clean it, you rub something off, and one of them is rubbed off 40 times in going around this protocol for the 40 nations, and the others are rubbed off once. So the K is getting lighter. So there's going to be a big deal. You're going to hear about values for Planck's constant and experiments, how you're going to make the connection. So mass is going to go away. I'm talking about making length go away. Michelson got a Nobel Prize for measuring that bar, the prototype of that bar in Paris using light waves. The lights that he had a Doppler line width, which is what you can see here. This actually is a laser output, but the Doppler process works just for that as well. So this is a few hundred megahertz for this infrared transition. And what I thought was noticeable were these super sharp lines, which are due to the saturation of methane that's in the same cavity. So it's sharp and narrow. It's a new kind of technology that made it possible for us to have interference fringes in a precision Fabry probe that are like this instead of like this with the standard. And it's not hard to decide which one we would like to go forward with. But there is a tiny question: what's the relationship of this wavelength and the one which we already know and have adopted? So that's going to involve some metrology. Here are some pals, Ken Evenson, Joe Wells, and there's 3 lasers out of the 12 or 14 that are involved in this chain. In these ancient days before 1972, we didn't have any comb that goes everywhere in one step. We had crystals or harmonic generators, and you could go factor 2. So you think about it for a second. The frequency of this laser that I showed you is 88 terahertz. And what the highest frequency we had as a standard was this 9 gigahertz for the cesium. That ratio is around 9,000. And we're going to get 9,000 by doing this process again and again. The right answer is 13 or 14. Because you have to step back a little in order to get the digits to come out right. So side by side in this lab and 2 more were these long lasers, and there's a guy for each laser, spectrum analyzer or phase lock oscillator for each one. It was serious work. There was 12 people, and thanks to you and your parents and your siblings for sponsoring this whole enterprise in the NIST. I think it really is a good thing for national labs. You don't work on all the problems, but a few problems that are really at the core. I mean, it used to be that if you wanted to do science, you would talk on the phone and talk to Jack in Athens and say, when you mix those 2 liquids, did it turn green or yellow? And that's a kind of information transfer. But nowadays we need numbers. We have to have a reference, and that's what this National Bureau of Standards is about, is trying to figure out ways that in Japan or Zanzibar or Caltech, for heaven's sakes, you would be able to make 10 digits or 15 digits or whatever is the appropriate thing. That is really interesting stuff to do. So this redefinition of the meter then came, we're trying to choose whether we're going to take the laser that was proposed by the Germans or by my Japanese colleagues or the French ones or the other branch of the NIST. And you can just imagine what it's going to be. I'll tell my chief, I really did a good thing for the United States today. I agreed on our behalf that we were going to adopt the laser that was proposed by France. Well, this is not going to sell well in the United States. So the answer is the physicists are going to find a way to wiggle out and use fundamental constants. So what's the idea here is that we don't need a standard length, for heaven's sake. We got the speed of light. What more fundamental thing could there be? So all you need is a number for that. And there's going to be a quiz as you go out. 299,792,458 meters per second exactly. So that happened, and this lamp that the style that Michelson used was made obsolete in '83, and the meter was redefined in this way. Now what I'm going to tell you about is what's happening then in the wider space. So we, as primary units to measure time, length, mass, temperature, electric current, light intensity, and amount of material. That's enough to describe physics and chemistry and all the stuff. But maybe you don't need that many. You don't need 7. We just found out how to do 6. And how would it be if you had a buddy like von Klitzing who says, I can tell you how to get ohms. It's easy. You put this crystal in the cryostat and control conditions exactly right. And it's 26 kiloohms, and there's a lot more digits. And okay, so we don't need something else. And then what about the voltage? Well, you can put your signal generator on the Josephson tunnel, and it makes a little voltage step, or if you start with this voltage, you can see the frequency. So this business, well, we're working ourselves out of a job, is what it really going to be. When we finally get done, the thing that's going to really cut the mustard is this one. We can measure everything best by counting as digital clicks, or the analog part at the end, the phase extra. So that's going to be a cool story, and unfortunately, I am maybe probably will have to retire. But I really believe in time. This has brought home to me pretty emphatically. This is one of my wife's favorite clocks. It's a standard definition in our home. And the way that you find out how it works is you come home late. So after there's this really unambiguous communication of family life is tense for a moment, but everybody goes on better. So in trying to get standards, of course, our caveman predecessors could notice the day and night alternation, and that would be a natural thing from minus infinity or when 6,000 years or whatever you believe when it started. This is pretty nice, except that we have storms, and that changes moisture from sea level up, and that changes the moment of inertia of the Earth, so the conserved momentum has a different speed, different RPMs for the Earth, and it's a few milliseconds. So these brilliant people who were only interested in things that have yearly and longer timescales in 1956 said, okay, what we're going to do is use the Earth orbit around the sun. That's a really good thing. And we're going to buy a factor 365 in a scale. Now I point out to you that in this clock, you get 1 click per year. And that's just in the time when these aggressive electronics companies that are in this Los Angeles basin are selling 45 and 90 gigahertz radars to the military. And when I said gigahertz, but I mean, that's right, gigahertz. So it's such a huge factor. It's just completely hopeless. This is not useful in the slightest. But probably the gravitational radiation from this is very slow. So maybe this is not a bad clock if you don't mind waiting a little time to get your clicks. So the thing which is, of course, the real marvelous thing was to introduce atoms. Cesium atoms, a pretty good one. It has this hyperfine interaction. So as I say, it's 2 milliseconds. That's parts in 10 to the 8th. For this one, it's a free factor 365, a free meaningless factor. And when you come up to here, the frequency is increased by some important factor, 10 to the 14th. And so after 1955, Essen's proposal to use cesium was taken. Proposal for the first maser was from Charles Towns, and they used ammonia. And that's part of what his Nobel Prize was for. Well, I've apologized for my pictures because that good was up on that picture, and all the other pictures I'm going to show you now, good is down. So this is in something, nanoseconds per day we could start out with. So it's 10 microseconds with this ammonia clock. And then as we go along in these years, it gets little by little better and kind of has a slopey, and this is log and this is log. So it's roughly 10 times in 10 years. And that, let me just mention, is the hard work of a bunch of guys. Maybe your National Bureau of Standards has 10 or 15 people who work just on primary standards. And thank you for sponsoring us. So laser-cooled thing is started here in the 90s, and that had an even bigger impact on optical things. So this, you could think of this as sort of the center of scattering around about different proposed optical systems, and they really didn't amount to much until some really critical ideas like slowing atoms down and increasing the density and using more. But anyway, you keep going, and this fountain idea came that improved by one step. Jim Berquist got very nice results at an early time with a single mercury ion. Junyi and I and all the right-thinking people, many of the right-thinking people think that it's better to use neutrals because, as I'm going to show you, you can have lots of neutral atoms together, but the ions have this long-range force, and then they interact with each other, and they're no longer independent ones. So when you add them together, you get interaction physics as well as a bigger signal, and that's going to be hard to deal with. So strontium actually has the highest Q and signal-noise ratio of what we have. So I'm sorry that I have quite a bit on this picture, but let's start over here on the left side. And this is sort of when my technical life began, 1960. For example, these two things, the Ted Maimon ruby laser in May or April maybe, and this Javon laser in December. Well, I didn't even know about the Javon laser because 6 days before that oscillated, Lindy and I had our first son. And you know, this, I don't know, I was interested in other things for a while. But it was obvious that there was something about this. This is a continuous laser, it's running continuously. These are pulse lasers, they go whap, and then you wait a while and you can do it again. Well, it's pretty fun. You can store up a joule or two and get that out as light, and it'll burn a whole razor blade. And I could do that, and it's pretty nice. It makes a spark and a hell of a noise. And the thing then is, what is going to be my achievement at age 35 and 45 and 50? Maybe I can do 137 razor blades. That'll be my penultimate. And this is not a good highway for that kind of a boy. But other people took an interest in this, and you know, you can get kilojoules and lots more in a valley over not so far from here of light. But then people started fooling around with the idea that, okay, I like to study pulse lasers because they have high power and we could do nonlinear stuff, but wouldn't it be great if it did a couple of pulses per second so I could see it? Well, that's actually too slow. How about 10%? How about 1,000? How about 100 million pulses per second? And it's just going. Now that's hard to tell with your eye that that is not a continuous laser. And on the other side, we have, by that time, the solid state laser technology and produced really nice stable lasers. And in fact, you can go back and forth across this boundary simply by messing with the adjustment of your Ti-Sapphire laser. So what's the deal here? Is this boundary real or not? And this is where the combs business comes up. After you understand how to have organization in the pulses, that's to say they're equally spaced and equally tall, then you can be completely comfortable going back and forth, and you can talk about the pulse power that's here, or if you go up here, you can talk about your 1 million laser lines that are 1 hertz wide, and they're separated by 100 megahertz or whatever. This optical comb is something which has just been waiting to happen. I was lucky to be able to participate in it. The thing that made it possible, at least this is now in the discovery phase, is exemplified here. This is a micrograph of a fiber. You know, glass fibers that we use are the same kind of diameters we wear around on the top of the head. So this is really magnified, and this is only 1.8 microns across here in the center. And that looks like a place where when Wendler was building this glass, he stacked a rod and then a tube and a tube and a tube, and you get a whole thing like that. And finally, you get about this much glass together, and you put rubber bands around it and take it to the, this is pretty festive. Is this how you control the speakers that go too long? I don't.
You are not going to talk over today.
Yeah. Okay. More dark is good. I do like it. Anyway, the thing that's important about this is that the light is confined in this center thing. And it's confined because the neighboring material is air. So that's a huge index differential, and you think about the glancing beam and the Snell's law reflection issue. Having air around it makes it possible to confine the light much more tightly than it was if you just had graded glass. The other thing is the field doesn't go to zero. It's in this one and the next one and the next one. So you can mess with the design of this a little bit. So packing density, hole size, and web size are parameters. And the consequence is this is a designer space for adjusting the speed of the optical field that's in this central fiber so that it has zero dispersion. Whatever color you put in around, in this case, 800 microns, goes the same speed. Now that's pretty important, because if you take a big hammer laser power and put it into here, I mean, we start with something which is a part of a watt, and then these pulses are coming, and they're compressed by 1,000,000 to 1. Almost all the time there's no light because all these frequencies interfere to 0, and just every once in a while you get this pulse. And so you go from 1 watt to some part of a megawatt going into this, and this is only a micron. Now, dudes, we're talking about serious power density. In fact, the electric field that goes with that shakes it with a strength which is like 1/3 of the electric field that's holding the atoms together and the molecules. So it's not surprising that a few nonlinear processes happen. So what happens is you put in some spectrum. This is wavelength and outputs in a log scale. Here's what our laser made, and here's what you get out of that fiber. Vastly broader. If you look at it with your eye, you know something really important has happened. It's really, really spectrally broad. I don't see out here at the red color where the fundamental power is. We can't see out here because of the eye cutoff, but there's plenty of UV. So this became known as the magic rainbow fiber, and really a good kind of thing. And at first it's really hard to do, and you have to wheedle with your buddies at Lucent, and they're discussing with their lawyers, and finally I got a envelope written in primary school lettering, no return address and nothing in it. And well, okay, I'm not quite sure what's the deal, but then just before putting it in, the light happened to glance, and I thought, oh, there was something in it. It's some little whisper of glass. So one of these Bell Labs guys was kind to do the right thing, and so we were able to get this going. And this was a fantastic story of cooperation and competition. Dr. Holsworth was a student or postdoc in Ted Hensch's group. Thomas Udom and Scott Diddams was in the same relationship with me. So those guys went to Germany to learn everything that they were doing, and they sent one guy to Boulder to learn all of our stuff. We just marched down the highway together, and that way you don't ever hit the rails, so you get feedback by other people's knowledge. It was total joy. Ted and I are good buddies still. So this comb is a really nice thing. You've undoubtedly seen all of this kind of stuff. I was totally pleased to be able to design some electronics where you could click, divided it into 16. So each pulse that comes, the phase will advance a little bit, and you could choose whether it advances 1/16 or 2/16 of the whole cycle. And that's kind of interesting if you play with extreme nonlinear optics, because probably it's going to make a difference if this electric field lines up with the envelope peak. So then you get a bigger action and symmetry and all the rest of those things. Anyway, this worked out really nicely. In the end, what that thing turns out to be is that it's a connection with no slippage. These are phase-locked gears, and they let you transform between one frequency and another frequency. And it doesn't even matter if the radio frequency is 10 to the 6 times smaller than the optical frequency, or you could put another gear on here and gear off another optical frequency. So it's just coherent and occupies like factor 2 of bandwidth. You start at F and you go plus a half and minus a half, and it's, if your color's not in there, it's pretty close to, there's another one that you might be able to use. So that led to the issue of trying to understand how good were the lasers we were making, which are these green neodymium YAG stabilized on iodine. And so we could take our frequency in the optics and compare it with a microwave by using this thing as a gear down. So we connect it to the best commercial cesium that exists, and we find beats that are better, 10⁻11 at a second, better than HP said their box was. Well, that's because that was HP in the old days. And they, there was a big margin. And then that has a white noise in it. But what's important for experimenters to notice is that this keeps going down with square root of tau. And it's so nicely designed and so well evolved that you don't come to a flicker place where it doesn't improve anymore until you get to a week. So it's still possible to do seriously accurate measurements with this portable thing. It only costs $63,000, and you can have one for your own lab or airplane or whatever you want. But the NIST has an ensemble of masers, and those have been studied, and they have different time scales where they have problems. Temperature controller problem for one, and magnetic shield problem for another, and one by one you can fix it if you have a lot of them and make all across measurements. And so we made a beat against that, and that's what this is. And then what I'd like to point out is that if we compare against a second version of our own thing, it has less noise. So this says, oh gosh, we're doing better than the best of my NIST buddies have been able to do. But it's easy for us because we're walking into a new space, and you just have to not make big mistakes, and you're going to get there. Well, the progress in this business is basically exploding, and there are new ideas. For example, here is an atomic fountain. Atoms are cooled, cesium atoms are cooled. The laser below it gives it a burst. The atoms go up maybe a meter. They go through this microwave cavity and get coherence written between their hyperfine states. Then they go on up, and then they come back. This artist didn't make this the way that I asked, but anyway, I wanted to show these were really going up. Anyway, they come back and through the same place, and then you can read them out. So this is called an atomic fountain clock, and it lets you get into a pretty nice place down here. It's now at the 3 or 2 times 10 to the minus 16. Another kind of technology that's good is this trapped ion. You can have one nice ion there, and the laser shines on it, and you can find the center of it, and you would like a line width, which is maybe 1 hertz or 3 hertz or something. It takes a moment to cool it. So you're going to be able to cycle this once a second maybe, and then you get 1 point. Or another way would be to have an egg carton, an optical lattice, and fill it up with individual atoms, and then you've got a real good thing going for you, because if you have 5,000 atoms, the fluctuations are square root of 5,000 reduced. So that's really a big process. So here's how this picture has gone then. The cesium has gotten better, 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 and then bang, no more progress. And the optical businesses have been coming down, 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 down. And then we start to wonder whether there's some way to organize this or see what the future is. What factors are important in this? Well, the trapping and cooling of ions, everybody could understand that that was important. People in Sweden did too. Cooling atoms with laser lights, Chu, Cohen Tanuji, and Bill Phillips, that was immediately shoe-in. I mean, look at this, 89, 97, that's not very far apart in time. And then there was enormous progress in the laser stabilizing business. This hasn't been out on the for sale long enough yet to wonder whether it's going to get rewarded. But this guy, Mike Martin, is the right kind of a guy. I think he's actually in the valley here enjoying his life. He was the one that said, oh, let's use the atoms as a spectroscopy tool. You know, that this Ramsey fringe business, you put on 2 pulses and they have phase relationship between them, and you get plus or enhanced or get sinusoid fringes. But what happens if you put on another pulse in the middle? Then you could add on plus 2 pi or minus 14 pi or whatever you like. Then you think about this time domain of pulses. What would it look like spectrally? And then this is some kind of spectrum analyzer. So then you can take the laser and see what's the fraction we can get of the atoms into the excited state. And that lets you figure out what the line width is. An answer which they publish is 0.028 hertz, which is pretty impressive for an optical frequency. And then this thing that happened to Dr. Hench and me. And now the next big thing which has come on the scene is a collaboration of Katori in Japan and 2 dangerous guys, Jun Yi and Jeff Kimball. So this idea of having the same interaction strength, So I indicate I'm not sure how this is going to turn out. But here's the idea. If you had an energy level, and the optical transition we're going to play with is this one, and then we have a laser beam which is localized in space. So the laser beam is just this wide, and so what's going to happen? Well, it interacts with the atoms in that ground state, makes virtual excitation into excited states, and for the wavelength that's chosen, it pushes the levels down. And so now the atom is in this kind of a potential well, and you know what atoms like to do in potential wells. They find a way to have it quantized and vibrate, and then there's a half a vibration unit at the bottom for if you still are enjoying that extra factor of a half. In the excited state, in general, the light couples you to all different energy levels, but they depend in a different way in wavelength. So the really smart ideas that those three gentlemen had in some linear superposition was that we could find a wavelength so that you would get the same potential well in in the excited state and in the ground state. So that means that it doesn't matter where you are, how much light you have on it, the difference between these two is not changed. And that's really an important concept, because it means now you can hold these things against gravity and they just sit there. If you do a good job on the vacuum, they could sit there a long time. If you did a better job on the laser, they wouldn't have boiled out at 10 seconds, they would still be there in half an hour. So this confinement with laser cooling can be so small that they don't explore very much of this well. And so there's hardly any phase shift of the light as you go across it. So, and that gives you this improvement by the square root of n. So you get the normal scale for any kind of clock that has a resonance Q, and the square root of n. So long coherence time, no Doppler effect, no recoil shift. And the only question is, if you start jamming a lot of atoms into one of these cells, maybe there's going to be some collisions. So everyone is talking about, oh, this is some kind of a pressure shift. I'm starting to not like this again. And Jun, I absolutely love him. He says, no, this is opportunity, man. You say there's an interaction. I'll turn down the rate of exciting it, and then that interaction will be resolved because we have a longer time. And with that longer time, we have higher resolution. So all this is just another set of substructures, and we can figure out how they work. Well, it turns out that strontium has a little bit more spin than we really need, 9/2. And so there's lots of levels, and so that makes it lots of states, but it completely doesn't make a difference. Another good way of getting them, if you had one-dimension lattice, these are like little pancake disks, and the atoms love to be where it's bright, so they're all jammed up close together in these disks. But if you did it again from the side, then you'd be able to have those little wells that I showed you. And obviously ones are going to be able to do it in 3 dimensions as well. So finally, the next step then is you've got these atoms in the trap. You've got a nicely controlled laser that's shining on it. You make some transition which results in optical output or particle output, depending on what exactly you're doing. It goes into some mechanism that's got a comb inside it. It's got some software, probably 6 or 7 graduate students that are writing code, and its output is a clock indicator, and it's also an optical field, which is the comb is geared down so that it's in the communication band, so we can send it over to our buddies at NIST and see how we're doing. So that's how the frequency gets measured. And when the frequency was measured the first time, let's see, red is Gilla here. So that's an uncertainty of, oh wow, these are only hertz. So uncertainty of 12 hertz the first time, and then measured in the National Laboratory in Paris, and then in Tokyo, and smaller, and this ends in 2008. So now where one is the case that I want to talk about. These things are working better than the time standard is. So if you're going to measure anymore, we're going to have to do more work. I'd like to say just one or two more things about the technology of this. We're talking about optical coherence, and so here's the mind's eye view. You're going to have a mirror, and then there's going to be some coating on it, and then there's a tube spaces these two mirrors, and the field is captured in here for maybe 300,000 bounces or some reasonable kind of number. And then the leakage field is what we're going to do the experiments with. Now, that's the dream, but and it's interesting to think about what the numbers are. The cavity length is some part of a meter long, and this precision that one has of the variations of the length is around 10 to the minus 16. So 10 to the minus 16 is smaller than the size of nuclei. So this thermal motion is not completely small, but it's kind of small. So anyway, in some kind of artist way, this shows that there's all kinds of modes, thermal expansion, vibration modes, expanded on these discs that are, 3 centimeter in diameter and an inch, a centimeter thick and an inch in diameter. And so here's maybe how the surface looked at just one click of the camera. So mirror thermal noise is a fundamental process, and even if you have a 4 kilometers long baseline like the LIGO people do, this is still the noise limit. So how do you get it less? Well, you make it longer. But if you make it longer, then the vibrations of the floor are going to bite you because nothing is stiff enough. And so here's again a case where wonderful Mike Martin said, no, I understand how to do this. You guys told me that if you hold the cavity, so the light's going to go up and down between the top and the bottom mirror, if you hold it in the middle, the gravity will stretch this out and it will compress this top part down, and so the net is almost zero. And you know that gravity and acceleration are the same kind of animal, so this says this is a vibration insensitive cavity relative to vertical vibration. Now, that's a really nice idea, but I kind of don't like to have it vertical because that's the way the gravity is working. If I went this way, then the gravity would just squash this a little bit, and then it would be more like squeezing toothpaste with the gravity and the vibrations we're doing. But I've lost my symmetry. So good old Mike started figuring out how could he drill into this bar. Here's the mirror and the light path. So you're going to end up with this bar of stuff, and you're going to hold it. And you know, Mr. Airy got famous in 1800 for finding the mounting points so that this bar had the ends that stayed parallel. And that was really important because the meter bar, you want to be able to measure its ends flat. But now Mike has added something. He says, how far apart should these two fingers be that are going to hold it? And then how deep should we go up towards the center? Because if we got near the center line, we'd get to use your symmetry principle again. So the result is that this is factor 30 reduced vibration sensitivity. And that lets you have it be so long, and then the thermal noise in the mirror is not so much. So this is actually the best local oscillator that we have at the moment. I'll show you in a moment its picture. It's 1 times 10 to the minus 16 out to 500 seconds. So there ain't nothing else that is like that. So this means you can probe the strontium atoms more precisely. You know what it is that you've asked them, and then the noise is less, and you're going to start from someplace here. Well, let's see how that turns out. So I guess I have this in a different order. So let's just talk about where we are at this point. We have 60 years invested in at every slice along that time. The cesium clock has been the best standard, and it defines time ever since 1967. And by time, it's international second and the inverse second, or the hertz. And with nice ideas and seriously hard work, there's continuing improvement, 6 orders of magnitude over 60 years to present 16 digits. That's a little bit stretching. It's maybe 2 10 to the minus 16 with a cesium atomic fountain. However, these laser dudes walked in 2008 with this optical clocks, and 3 of them became more accurate than the time. So this, you realize, oh, this is a phase transition. We are entering the start of a new place. What are we going to do? So trapped ions, you've got lots and lots of ions to choose from, neutral atoms in optical lattices, strontium, terbium, calcium, mercury, and magnesium. And so now we get to where my headache comes up. Do you think these things are all going to be in sync? I mean, they have a different frequency, so we'll take that factor out. But if we go a year in advance, are they all going to be keeping time at the same rate? And what the name of that topic is cosmology. And here we are on a tabletop, and we're doing stuff that you can't do with LHC or with a big telescope, and I love it. Atomic physics in the lab. So here's what Berquist and his colleagues did. They had one system set up with mercury, a cavity, and you get a wavelength that excites the mercury transition. You have aluminum, another really nice clock, different wavelength that excites that, a comb that connects them, and then you end up keeping track of what this frequency is and the frequency ratio. So this is the frequency ratio -1. Oh, and it's expanded quite a bit, 17 digits. So here is what they got from 2006, 2007. And, you know, for first order, honest assessment would say, okay, there's no evidence for any trends in this. And so we're going to say that there's no change. If we made a plot of that, there's a measurement possible also against cesium. Cesium brings in the magnetic moment. So in one axis, it's the change of cesium and magnetic moments, and the other, it's this fine structure constant. That's the 1/137 stuff. And here is the place which is allowed. And it's way close to 0. Except you look at this and, oh man, I mean, I hope all of your hearts beat and say, oh, let's do this longer. This is 2008. What's the data like now? Well, not so fast. Let's see, where are we? Is the fine structure constant at this point? So at the present rate, what this limit corresponds to is it would have changed by a part of less than 1 in 3 million across the age of the universe. So if you're a betting person, this steady is a good one to bet on. However, if you look on the archive, look at this latest result, not yet refereed, I believe. I'm not positive what its status is, but please notice where 0 is. This allowed circle doesn't include 0. Yes! That would be an absolute breakthrough, that our universe is still evolving. We had a Big Bang once, and cool stuff is still happening. I don't believe this is going to hold up, frankly. But we'll just see. You'll just see. So let me see. I've got, come on, don't fail me now. So then other kind of things, Dave Wineland's guys, I think, are not supervised carefully enough, because they thought it would be fun to take the aluminum clock and this other mercury clock and put one of them on the table with a hydraulic jack and lift it up. And what's going to happen? Well, the gravitational potential from the Earth will change, and the frequency changes. So here's general gravity redshift right near own lab, and this took quite a bit of time, and each one of these data points is 8,000 seconds. And well, okay, that's because they have a little bit too much noise, but if you improve the clocks like I'm talking about, lifting a clock by 35 centimeters changes its frequency. That's unambiguous. But with June's latest result, June Yi, strontium lattice clock, the specs are degraded by a factor of 2 for 2 centimeters vertical error. So this is getting to be kind of an interesting place. What does that mean? How can I have clocks. Let's talk just for a second what's involved in getting the clocks to be good. Here's his amazing 10 to the minus 16 clock presented in a different way, and then you have the resonance, and then you get a square root of time averaging. And this is 10 to the minus 18, and let's see, 10 to the 4 seconds is a couple of hours. So in a day, you're going to hit 10 to the minus 18. And the kind of things that you have to look into is black body thermal radiation, density shift maybe. Might be some Stark effect from the probing beam, maybe some magnetic field or second order Zeeman, or there may be some issue about your polarization, and blah, blah, blah. Thousands of interesting or semi-interesting things that you can take into account. What they claimed in this paper 2014 was 2 10 to the minus 18 stability and 6 10 to the minus 18 accuracy. And then, of course, new things are happening all the time. The NIST Boulder guys are doing superb work, and they're pushing down. And another idea is that mirrors made of crystalline material, they're made by just growing atom layers, then that has less thermal noise, and so that's going to be a good thing. Our friends in Tokyo are just jumping immediately to running at 4 Kelvin. So this is going to be an interesting race again. So here's a paper which was published in April, which says we have studied all the systematic effects, and we're announcing that we can understand everything at a level of 2 times 10 to the minus 18. And the head author of that is Junyi, and the guy that's really put a lot of midnight hours into this is Mr. Nicholson. So I'd like to use this picture one more time. So here we created the definition of the second, and we watched it get more and more precise. All these new technologies coming down, and then we've got a couple recent measurements that are completely below this. So here is another way of illustrating this. If we could keep going on the progress rate that cesium had, we're way beyond it. So there's a problem. So in the future, a new standard of frequency and time is needed. And obviously the question is when. So one criterion should be, well, the progress should have slowed down so that it makes sense to think about making a permanent definition. Oh, I'm here to tell you that's not the case now. Progress is accelerating. What is proper is that all the candidate systems are getting evaluated. People really understand how to do this now, and there's no hype or, I would say, dishonesty of publications. And finally, the way that we make progress in science is to do stuff twice or 3 times in different labs and be sure that if it's made out of chemicals that we got in Verona, it's just perfect. What works the same as New York. Remote comparisons, how in the devil do you think you can do that? So here's the problem. 2 centimeters is what you need to know, and how are you going to go between clocks that are separated? Well, the first idea would be to rely on known and, come on now, well-developed technology, the GPS. The long and short of the GPS is that it's unbelievably excellent, and it allows you to transfer time to 10 nanoseconds or 3 10 to the minus 14. If we want to go from 10 to the minus 14 to 10 to the minus 18, that's a factor of 10 to the 4th. It means 10 to the 8th averages. That's completely more than a year. Let's think again. Another way is, of course, to look for these amazing Russian people who thought about this Molenya orbit, and it has this huge ellipticity. It's a 12 hours orbit, and after the 2nd hour and until the 10th hour, any one of these places can see 2 labs on the Earth, so you can do single source comparison. Now, the only thing I need to ask you about is, tell me when you have escape velocity for this thing, are you going to end up with microns per second Doppler residual, as there's going to be a spread in the definition of the angle. And I think this is really hard. I'm thinking about some static arrangement. And there's one more thing. We have the sun and this lovely place that we live. And okay, we know that it's not a circular orbit. So the first thing you think about is how big is the GR shift? Well, it's 10 to the minus 10 is the difference in the distance. It makes 10 to the minus 18. The redshift is 10 to the minus 8. So it's not a big deal, 10 to the minus 18. But there is something which is interesting, and that is that at noon, you're closer to the sun, and at midnight, you're farther away, and that is a change in the distance of 4 times 10 to the minus 5. So with this 10 to the minus 8, you're in the 13s. And for the strontium clock, it's 180 hertz. Okay, now the way that relativity works is that this potential is common. So you go in your lab and you search for this 24-hour thing. No, you're not going to find it because all clocks did it. But I got an idea for you. What happens if you had a fiber that went someplace to where your buddies are and they would send you their frequency? If we organize the geometry right, we might be able to see it. So that's particularly interesting because the present precision is millihertz and it's 180 hertz. Well, we'll come back to that in just a second. So this idea of universal time, the answer is it's not going to happen. And that's the deal. You have to know what you're doing. It's not just look on what the GPS has set your watch to. So how do we transfer it? Well, we're going to do it with fiber. And the fiber is a fantastically beautiful thing. It doesn't lose any of the light, but it does phase modulate it if the temperature changes or if you vibrate it. So we had a nice thing, which I was astonished the NIST didn't think it was worth patenting. But of course, it's only the optical analog of what colleagues at the JPL do for their deep space network. But it is nice, and it's got some special features in optical. Anyway, we can take out this so that we can deliver the same phase in the JILA lab and see that same phase over in the NIST. And when we do that, we compare our laser in their lab, and we find the beat is a hertz wide. Well, it means you don't get a hertz by canceling vibrations. So it means mostly this is working okay. So the people, as soon as that got published, we got people from the astronomy community coming in because they had this fantastic telescope system being built in Chile. And the problem is you got to disseminate what the local oscillator is. So that's the best customer, that's, so to say, intellectual customer. There's not a penny has changed hands. The advanced light source people synchronize their klystrons with this kind of technology. And then there's, I don't know, 11 or 15 standards labs around the world that also do this, but they're completely not a big customer base, but they really care. So what you can do with 30 kilometers is a part in 10 to the 17th, and you can transfer with a 1/10 of a femtosecond, even in a wide bandwidth. Now, our enterprising European people are really lucky because in every country, the telecom is owned by the government. So now, instead of 100,000 telephone companies like you have to deal with in the US or in Japan, Germany can control, and a fiber is already in place that goes from Braunschweig to MPQ in Garching. And there's already sending canceled signals back and forth. This is a very useful length. It's nearly 1,000 kilometers, and it needs, or it could use amplification. Or is it okay if we just let it get weaker, 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 and amplify at the end? And so a lot of important research is being done by that. But what I saw in that was that with this picture in my mind, what about this fractional shift, these fiber-linked European stations? I mean, it turns out that where these labs live in Europe is all within 1 hour of the same time zone. So they're practically all at midnight or noon at the same time. So what's going to happen? Well, they're going to have a few stations that are up close here, and then a little bit later in the night they'll be over here, and the rotation's going to change. So it's easy to work out what you'd get. In Braunschweig, it's 157 hertz minus at noon and 44 hertz plus at midnight. And if you took the signal from Braunschweig to Torino, that's 45 degrees south, it's minus 166 and plus. So this big 250 hertz deal turns into 10 hertz, but the uncertainty is 1 millihertz. So I think, let's do it. So anyway, this is, and how did our French colleagues do? They said, we're not going to do this with our own fiber that we own and we have completely control of it. We're going to do this in a cooperative way with commercial signals that are already carrying telephones conversations. So they have achieved this for a relatively short length. Now there's papers that are being reviewed or in press that talk about 2,000 kilometer runs, either back and forth or something. And it's easy. What happens is it doesn't hurt much if it gets longer. If you don't let it get degraded, you just regenerate it and start again, and you get a little bit more phase noise, but nothing goes wrong. So what do we have as suppliers? Well, here's one company, Interroute Network, and they've got all these fibers going from Europe to other places. And I'm not sure they've got any dark fibers. And then there's another company, Internode, and that goes across the ocean with lots and lots of optical fibers. And the same story. I don't think they're filled up. And then there's other companies with all these fibers, and they even tell you in detail what their communications protocols are. But they're the kind that put repeaters in, and they go back to electricity and then a new laser. But it would be possible to go all the way across with 200 amplifiers, and you want to synchronize them so they all know what the 11 gigahertz Brillouin shift is that one is used. And here's another idea, this global financial network. Well, I'm guessing they're not going to help us at all. In fact, I don't know if everyone is acquainted with this nice book about the Flash Boys. So I'm going to wind up here in just a couple of minutes. The STAR mission is what I think would be a cool thing to try. Its purpose is to look at the gravitational redshift of an atomic clock compared with a clock that has a cavity. And here was the proposal pictures that were in the proposal that we submitted, and here are ideas about how you could send the light beam so you could get longer paths. This thing is going to go on the orbit, and it's got a cavity filled with gas inside, so we'll get resonances out of that, and it's going to need some nice locking. I figured out how to do this anti-residual amplitude modulation business, so that's perfect. So here is the spreadsheet that describes how that works, and on the third page, you just look here. If it was professional, it would be called the bottom line. But how it turns out is with just something which is this scale, you can do less than a hertz at a second with this gas absorbent, and I'm going to try that. And in fact, it's real, because here's what happens if you go into the lab. You can see something weird at the Doppler absorption is down. And here's something which looks for all the world like that peak that I showed you from 19 whatever it was. So it's like I was a new boy again. I'm ready to follow out a sharp peak, and let's see where it goes. Okay, I'll say just a couple of words about something which is technically important. Accurate removal of RAM, residual amplitude modulation at the part and 10 to the 6th level from a beam. It will be printed when this symposium proceedings finally comes out. And the trick is to have an in phase and an out of phase or quadrature phase system for making the servo. And try to finish this in a second. Here's how, this is my physics package for this star. This is the size of the physics package. Here's the cavity that's going to be in it. I haven't contacted it yet. Here's prototype electronics of optics fiber and microwave cable coming in. And I hate to drill into my nice Snoopy box, so I've got to get a new box, and then I'll do this. Anyway, that's what's going to happen. To get progress, you can't hold your knowledge up close. You've got to go to some place where there's research guys and a research environment and talk. And it sometimes helps if it's in the evening and they have something wet. So I remember this is 2005. I went there and it was light and we had our dinner and had a stack of napkins clean this tall. And when we went out, it was dark and they said, "You're the last ones out of here, please go away." But we had fantastic circuit diagrams and ideas on the napkins. This is my group in 2000. That's the last time we have had a nice picture. Scott looks pretty good there. And I would like to emphasize and be absolutely clear that everything that happened since like 2003 or 5 or something, when June came back from Caltech, is due to his efforts and his team. They're just fantastic good guys. This Wei Zhang is a person that if you're recruiting for faculty is going to be a fantastic good one. So we're to the end. I'm going to say thanks for your patience. I'm sorry it's too long, but there are some places that you can read a bit about what we've been doing. Thanks a lot.